Hey everyone, I'm Praveen and welcome to AI Sparks, where artificial intelligence meets innovation and excitement. On this channel, we spark curiosity and ignite imagination with AI powered insights, tutorials, and explorations. From machine learning to robotics, we'll dive into the future today. Let me start with a slightly uncomfortable question. If you're training a code LLM today, do you actually know which programming language is worth the most tokens? Or are you just spreading data evenly and hoping for the best? Because that's what most teams do. They treat code as a single thing: Python, Java, Rust, JavaScript, all dumped into one bucket. Same model, same compute, same assumptions. And according to this work, that assumption is quietly wrong. This paper runs more than 1,000 training experiments, different model sizes, different token budgets, 7 major programming languages, all trained from scratch. The goal is simple: figure out how code actually scales when you stop pretending every language behaves the same. And the first result is striking. Every programming language has its own scaling law, its own learning curve, its own ceiling. Python keeps getting better as you add data and parameters. Rust improves fast and then plateaus. C is highly predictable. Java sits somewhere in the middle. There's a real hierarchy of difficulty here. Why? Because languages encode constraints. Rust forces structure. Types are explicit, patterns repeat. That makes it easier for a model to learn quickly. Python does the opposite. Dynamic typing, flexible styles, multiple ways to say the same thing. Harder to learn, but incredibly rewarding at scale. Here's a useful mental model. Some languages are like textbooks: clear rules, predictable outcomes. Others are like creative writing: messy, expressive, open ended. Scaling laws tell us exactly which is which. Now let's talk about multilingual training. Because modern code bases are never monolingual. When you mix languages, something surprising happens. Some pairs help each other a lot. Java and C show strong positive transfer. JavaScript and TypeScript too. The model learns shared abstractions, not just syntax. But here's the pitfall: more languages is not always better. Python helps other languages dramatically, but Python itself can lose performance when mixed poorly. Multilingual training is asymmetric. If you ignore that, you can hurt your strongest language without realizing it. Then comes one of the most important ideas in the paper: parallel pairing. Instead of shuffling code randomly, you concatenate equivalent programs across languages. Same logic, different syntax. This gives the model an explicit alignment signal, and the scaling behavior is wild. Cross-lingual ability improves faster as models get larger. Even more impressive, models trained this way can translate between language pairs they never saw during training. Java to Go, Rust to JavaScript. The model composes translations internally using shared structure as a bridge. Now, the big conclusion: uniform token allocation is a mistake. Giving every language the same amount of data is probably suboptimal. Some languages deserve more tokens, some saturate early, some only shine when paired strategically. The practical takeaway is simple but uncomfortable. Scaling laws don't just tell you how big your model should be, they tell you how to spend your data budget. If you ignore language-specific scaling, you're paying full price for discounted performance. If you found this helpful, hit like, subscribe, and comment which agent system you want to build next. Stay sparked. See you in the next video.